Unmanned aerial vehicles have become an essential component in many wireless communication systems because of their rapid deployment, mobility, and flexibility. In terrestrial communication networks, UAV can act as aerial base stations by mounting mobile base stations on them. Therefore, they can be deployed to provide wireless communication coverage in areas with no network infrastructure, as in disaster scenes. In addition to that, they can be used to improve the terrestrial coverage in case of limited period events. Several researches were presented on the deployment of UAV. Some researches focused on the placement of a single UAV for coverage maximization, by finding the optimum altitude of the UAV, or by proposing a placement algorithm for UAV that maximizes the coverage using the minimum transmit power, or by presenting an algorithm for the UAV placement to increase the coverage with various quality of service requirements. One of the challenges that faces the UAV networks is the deployment of UAVs, with considering the co-channel interference. Research focuses on the deployment of multi-UAV for coverage maximization by using the circle packing theory, or by enhancing the power efficiency without considering the co-channel interference. The co-channel interference is considered in the UAV deployment in some works for throughput maximization and the analysis of the coverage area performance. In this paper, the deployment of multi-UAVs for coverage maximization in the dense urban environment is presented. The effect of co-channel interference is considered due to its importance in the performance analysis of communication. Using the stochastic geometry, mathematical expressions for the probability of coverage are derived using the proposed stretched exponential path loss (SEPL) model for the air-to-ground channel. The SEPL considers both the line of sight and non-line of sight channel. In addition to that, it simplifies the mathematical analysis. The probability of coverage is defined as the probability that the user signal to interference and noise ratio is greater than the threshold. In other words, a user is in coverage when its signal to interference and noise ratio from its nearest UAV is larger than the threshold, T. The signal to interference and noise ratio can be expressed by the receive power divided by the sum of the interference power and the thermal noise. The probability of coverage of a random user averaged over the network is expressed by the integration for r greater than 0, for the probability of signal to interference and noise ratio greater than the threshold, t, given r, multiplied by the probability density function of r, where r is the distance between the user and nearest UAV. The probability of coverage for grid model. The equivalent uniform density plane entity, EUDPE, method is used to model the grid network. This method is used for calculating the cumulative interference by replacing the actual network with an equivalent network, whose base stations are uniformly distributed with density, ρ, where the serving UAV is assumed the origin of the polar coordinate plane. This plot shows the coverage probability of a uniform grid network compared to a PPP network. The grid network provides a higher coverage probability than the PPP network. This can be explained by the following. In the grid model, the distance between a certain UAV and the other interfering UAV is not closer than 2r, where r is the coverage radius of the UAV, which is more ideal than the real network. In the PPP model, the distance between UAV is randomly placed, so both the serving and interfering UAV can be close to the user, which results in more interference power than the real network. Therefore, the PPP model gives pessimistic results due to the strong interference generated by nearby UAV. On the other hand, the grid model is optimistic, because the actual UAV networks always show a certain degree of irregularity. Probability of coverage improvement. Two methods are proposed to improve the probability of coverage, by reducing the other UAV co-channel interference. In the first method, SD method, the interference is reduced by decreasing the coverage radius of UAV and set a separation distance, d, between the UAV coverage area. The increase in separation distance results in an increase in the probability of coverage. In the second method, FR method, the probability of coverage is increased by using frequency reuse, where different frequency bands are used by the network. The reuse factor determines the number of used frequencies. Using reuse factors eta greater than 1 reduces the density of the interfering UAV which transmit in the same frequency. The reduction in density leads to an increase in the probability of coverage. Multi-UAV deployment. The multi-UAV deployment aims to cover a certain area to achieve a target probability of coverage. Iterative algorithms are proposed using the probability of coverage improvement methods. First, the coverage radius of a single UAV is calculated from the path loss equation. The required number of UAV to cover the network area are calculated by dividing the total area by the coverage area of the single UAV and approximated to the nearest integer. The density of the UAV's network is calculated by dividing the No of UAV by total area. The probability of coverage is calculated using the grid model, which gives the optimistic probability of coverage. Then, the PPP model is used to get the pessimistic probability of coverage. The actual probability of coverage is assumed to be the average of the PPP model and the grid model results. In algorithm 1, the target coverage probability is achieved by increasing the separation distance using SD method until the probability of coverage reaches the target value. Then the new coverage radius is calculated. While in algorithm 2, the target coverage probability is achieved by increment the frequency reuse number zeta using FR method until the probability reaches the target value. Algorithm 3 uses both methods, FRSD method. In this algorithm, the frequency reuse number is limited to a predetermined number. The algorithm will increment zeta till its limit. If the probability of coverage doesn't achieve the target value, it will begin to increase the separation distance. The algorithm, FRSD, improves the coverage area by factor, zeta, compared to algorithm 1, and saves the frequency resources compared to algorithm 2. A MATLAB application for UAV placement is developed using the proposed algorithms. This application is a standalone app that does not require the installation of the MATLAB program. The UAV placement app provides a solution for the air-to-ground path loss calculation, the 3D placement of UAV as air relay station, and multi-UAV deployment. This demo focuses on multi-UAV deployment. The first part of the application is the stretched path loss, SEPL, model calculation. In this part, the user can set the type of environment: dense urban, urban, and suburban. Also, he can set the other parameters of the path loss model: frequency, reflection coefficient, building height, and the UAV height. The output plot displays the coverage radius versus the allowable path loss value. In addition, the coverage radius can be easily found using the maximum allowable path slide bar. The second part of the application is to calculate the probability of coverage for PPP and grid models. It allows the user to set the network density by entering the number of UAV per kilometers, or by using the coverage radius from the SEPL calculation part, or by directly setting the value of the density. Also, it allows the user to enter the number of the frequency reuse factor, zeta, and the thermal noise value. The output probability of coverage is displayed versus the signal to interference and noise ratio. In addition, the value of the probability of coverage can be found easily using the signal to interference and noise ratio slider. The last part of the application is the multi-UAV deployment. The number of the UAV required to cover the area is calculated by acquiring the UAV coverage radius from the SEPL model part. The UAV are placed using a circle or a square packing. The user is allowed to set the target probability of coverage, signal to interference and noise ratio, and maximum number of frequency reuse for the third algorithm. The coverage radius, frequency reuse number, and coverage area percentage outputs are displayed in the output table. Also, the outputs before using the optimization algorithms are displayed. In addition to that, a graphical representation for the network is proposed that shows the network coverage area and frequency distribution.